I think there's a lot of reasons why those first moon landings were important. Partly it was just because it was the first time human beings had set foot on something other than the Earth, which is an astonishing thing in itself. I mean, the moon it's the closest thing to us in space, but it's still a long way away. So it was a huge amount of work and effort. But perhaps more importantly than just that simple physical fact of standing on another body, is that it inspired so many people about science, about technology, about the excitement of doing new things. And that still has an effect. You know, I mean, I was too young. I was actually not quite born when the first moon landings happened. But a lot of the people that I work with and who taught me when I was an undergraduate and so on, they were inspired by this to start thinking about science and technology and engineering as exciting things, not just sort of practical stuff that you do because you have to. And I think it's probably its most important legacy. The moon is a very cool thing. There's all sorts of weird things about it. One of my favourite facts, which is of no significance but I quite like, is if you take every other planet in the solar system and you put them next to each other, they just about fit between the Earth and the moon, but only just. And that's a pointless but fun fact. I always find that quite cool. But there are some other things which are perhaps a little surprising. We're used to looking at the moon in the sky and it always looks basically the same. And that's a little odd, because everything else is sort of spinning around and we see different sides of it. And the fact that we only actually see essentially one side of the moon there's some interesting science, there's some interesting physics behind that. It's all about tides and the history of the whole system. So that's a surprising thing which took us a while to understand. It's also slightly surprising, and we only discovered this in the 1950s, the other side of the moon looks very different. We'd always assumed that, okay, there's only one side pointing towards us, but the other side's going to look basically the same. It's going to be a mixture of sort of paler mountainous areas which are very high, and then the low-lying areas which are much darker. We call them the Mara, the Latin for seas, although they're nothing to do with water. They're actually dried lava beds, dried up rock. But we assumed that the other side would be exactly the same, but it isn't. It has the mountains, but it doesn't really have the Mara. So there is actually a fundamental difference between the two sides, and that helped us to understand how it ended up with one side pointing towards us. It turns out that because it's got those low-lying plains, which is a denser kind of rock, it's harder and heavier than the lighter rock on the mountains. One side of the moon is slightly heavier than the other. And that's the side that ended up pointing towards the Earth because of the tidal effect of the Earth constantly pulling it and nudging it and tweaking it until it ended up stuck pointing towards us. Obviously, other planets in the solar system also have moons, and some of those also do the same thing as our moon. They point one side. And it depends on how strong the tides are. So the big moons of Jupiter, they pretty much all point towards Jupiter, because Jupiter is huge and its gravity is huge, and therefore the tidal effects are enormous. But some of the smaller moons going around smaller planets, they don't. They just spin quite happily because the tidal effects have never really been strong enough to lock them, so that they always point one side towards the other. It does take a long time. I mean, initially the moon didn't point one side towards the Earth, it was spinning too fast. And it was also a lot closer, and they're connected. So the Earth's tides have gradually slowed the moon down as it spins. But at the same time as it slowed it down, it meant that it drifted further away. We call that conservation of angular momentum. Basically, the total amount of moving in circles that something has is fixed. So the Earth is spinning, the moon was spinning, and the moon was going in a circle. And as the moon slowed down, so did the Earth, and the moon moved away from the Earth. So it used to be closer, and our days used to be shorter. And we've slowed down, the moon has slowed down, and it's moved further away. And that's happening with all the moons in the solar system, but it happened quite quickly with the Earth and the moon because it started off close and it started off big. The fact that we get really nice solar eclipses is purely a coincidence. The fact that the moon looks the same size as the sun in the sky, and therefore we get these beautiful eclipses where the sun is perfectly blocked but you still get the corona around the outside, that sort of glowing halo, that's a coincidence. You go back 100 million years, the moon was closer and it would have blocked out more of the corona. We go a few 100 million years in the future, the moon will be further away and we won't get nice eclipses again. We happen to live at a time where the moon is exactly the right distance and size to give us beautiful eclipses, but it's just a coincidence. We're very lucky. We do know that there are significant effects from the phase of the moon on quite a lot of living things. There are certain animals, sea-based animals, which always come to the coast at full moon, for example. Turtles lay their eggs at full moon, that kind of thing, because they need the light. So they're tied into those phases quite strongly. Plants respond very strongly to the phases of the moon as well in some cases. Humans, it's likely that we do at some level, but we've kind of we control our situation so strongly now. We have artificial light. We don't respond to even day and night so much as we used to, even 100 years ago. And so we've probably smothered over the effects that the phases of the moon have on us, and they're less noticeable, but they're probably there somewhere. It's evolution tends to use whatever it's got to get an advantage. And if something's easier when it's bright at night, your body will be more ready for those when it is bright at night, and that tends to be around full moon. So it would be a shock if we didn't change in some way. I mean, we haven't been back to the moon for a number of reasons. The biggest reason is it's very, very, very expensive. And so you've got to have a very good reason. And the good reason in the 60s was America wanted to beat Russia and Russia wanted to beat America, and that was it. That was the reason. There were no strong scientific motivations behind this. Nobody's going to spend that sort of amount of money and effort just for the scientific returns we got. A lot of the science that was done in that could have been done without sending people. It could have been done by sending robots and satellites and that kind of thing. So the main reason we haven't been back is it hasn't been worth the money and the risk. It is also dangerous. You know, if we push very hard to go back to the moon, there's a good chance that some people will die. And that's almost unavoidable at some level. So that's, again, why take that risk when you don't really have to. There's now an increased push to go back to the moon for a lot of reasons. Long term, people are looking at it as a place of resources. There are minerals which we could mine on the moon, which are quite hard to get at on the Earth, for example. So there might be a financial incentive. It might suddenly become profitable to go to the moon, although not for a while. But also it's a very good staging post if you want to go further out into the solar system. So if you want, for example, to put people on Mars, you can try going straight there and that's fine, but it's actually easier to go to the moon, set yourself up on the moon and then go from the moon to Mars, because you don't have to climb out of Earth's gravity with everything. And you can take water from the moon rather than taking water from the Earth and things like that. So people are starting to look more seriously at the moon as a kind of staging post to other parts of the solar system, like Mars and the nearby asteroids and things like that. Oh, there's vast amounts we don't know about the moon. We have a guess about how it was formed, but we don't know. We don't know exactly what's happening right down near the core of it. We're pretty certain it's not like the Earth's core, it's not liquid. The mantle of the Earth is liquid, the core is solid, but we're pretty certain that's cooled down and solidified on the moon. But we don't know exactly what form that is. We don't know all the details of the mineralogy of the moon. We don't know how much water there might be hidden on different parts of it. There's vast amounts we don't know. Always lots of questions in science. That's the best bit. The idea of aging at different rates in different places is a tricky one. There are physics things behind this. For example, clocks go very, very slightly different speeds when you change gravity. So technically, yes, if you're on the moon, because gravity is lower, you would age slower. But it's like a millionth of a second per year less or something. It's not exactly significant. But there are other effects. Your heart is having to work less hard because it doesn't have to pump blood from your feet to your head against a stronger gravity. So it's likely that there will be effects on your heart. But on the other hand, there's negative effects on your muscles because they don't have to work as hard and therefore they waste away. Astronauts find this when they're in orbit for long periods of time. So I don't think it's clear whether it will be beneficial or not to be in the lower gravity environment of the moon. Pragmatically, you would think that, you know, evolution has designed us to be in Earth's gravity, it's designed us to be in Earth's atmosphere and all this sort of thing. So you would expect any change to be for the worse. But maybe not. I mean, maybe just the simple fact that when you're on the moon, all of the air you breathe will be very carefully controlled and purified, means that we're not breathing in pollutants and therefore we'll live longer. Nobody knows. It'll be exciting to find out, though. I think the moon is a very inspirational thing because it's mysterious. You know, it hangs there in the sky, but you can't touch it, you can't get to it. It's a beautiful thing. It's always been, you know, a mystical thing to people than of seeing things by moonlight. They look different. You go out at night and the moon is up and everything looks a bit strange, it looks a bit weird, a little bit ghostly. And since we've had telescopes, being able to look in detail at the moon, it's endlessly fascinating. As an astronomer, I sometimes find the moon annoying because it's bright, and when it's up it's quite hard to see the faint things that you really want to look at. So for many years I was just kind of, oh, the moon, what a pain. But then I actually started looking at it, just with my own little small telescope, and it's beautiful. And you can watch it for hours and see the tiny changes as it slowly, the phase changes, and you get light glinting off the top of a mountain where it wasn't an hour before and things like that. And I could watch it endlessly. It's a wonderful thing. Ever since I was really little, I've liked asking questions. And I haven't stopped. I'm still basically 10 inside. And that led me towards science, because science is about answering questions, particularly questions nobody had ever answered. Why specifically astronomy, I'm not sure. It may have had something to do with when I was quite young, I was lucky enough to very briefly meet Carl Sagan, and although I don't remember much about it, my dad tells me I was very, very excited. And I think that's probably leached into me in some way, and that's got me going in astronomy.